Hi guys, so let us start today's session. So today is the final week for our course, and we'll follow it up with the usual sense. We'll start with the discussion for the course content, and then we'll solve the 12th assignment, that is the last assignment. Okay, so let us start with the discussion of week 12 content. And if you have any doubts in between, please feel free to stop me. So let us start with space vector pulse width modulation generation. So there are a lot of pulse width modulation generation techniques. Basically, in any converter, when you want the converter or any power electronic converter that is made up of switches and energy storing elements. And when you want these converters to operate in a desired way, you turn on and off these switches in such a way that you obtain your desired waveform. And in order to turn them on and off, you give them gate pulses. Now there are a lot of methods available in literature in order to generate these gate pulses. And so pulse width modulation is one such method, and the space vector modulation and sinusoidal pulse width modulation are subcategories of that of the pulse width modulation method of giving a gate pulse to the switches of a power electronic converter. So here, just specifically, sir has picked space vector modulation just for demo purpose, but you can apply the same concepts to other methods that are available. Okay, so we'll just look at briefly about space vector PWM generation. So if you talk about the discrete implementation, then in space vector pulse PWM generation, you take three-phase voltage reference signals and you give it to the PWM block. And the purpose of PWM block is to generate modulated signals that are then given to the gate drive that are later on given to the switches of the power electronic converter. So that is the purpose of pulse width modulator block. So if you see in this diagram here, we are giving the reference modulating signals as VA star, VB star, and VC star. And then based on those reference signals, we are able to generate the gate pulses for A phase, B phase, and C phase respectively. So what we are exactly doing here is, if we just take this particular slot here, and since in pulse width modulation, it's a high frequency modulation kind of method. So in this modulation method, we assume that the frequency of the carrier wave is much higher than the actual frequency of the converter. Okay, so if you just a second, yeah. So if suppose this is your sine wave, then the frequency of your carrier wave will be something like this. It will be very high frequency. Okay, so if you just consider if we consider those high frequency signals here, then you will observe that if a high frequency carrier wave is superimposed on this and we take this particular slot, then you will see that if this is that carrier wave which I was talking about, the high frequency one here, which is shown here, in that particular time period of one carrier wave, you can assume that the value of these reference or the modulating signals will remain almost constant, because I am varying these carrier signals at such a high frequency that in one cycle of this carrier, we can assume the modulating signals to be almost constant. Okay, so therefore, at this particular instant, I am taking the magnitude of VA, VC, and VB, and I am imposing them on the time axis here and obtaining these pulse width modulated signals. And similarly, by applying the triangle law, we can obtain these relations also. So this is just simple slope equation. Slope is equals to y by x. So using that similar properties of the triangle, you can obtain these equations. So once you have obtained these equations, you will realize that there are three types of different types. So this is the time period of maximum pulse width, this is the time period of minimum pulse width, and this is the time period corresponding to the medium pulse width. So this was just at one instant. Now when you vary from one instant to another instant, these phases which is having maximum pulse width and minimum pulse width will keep on varying. So you will have to determine that at that very instant which is the maximum and the minimum time period. So in order to calculate that, you use these equations. Now, when you talk about these time periods, there are different time periods which are assigned. So T0 is corresponding to the zero state, and T1 and T2 are corresponding to the non-zero states or the active states. So when you talk about in this diagram, you have seen that TA is this time period. This TA obtained here. This is TB and this is TC. Now, T1 is the time from maximum value phase to mid value phase. So T1 is here, maximum to mid value. So this is T1, this is T2. So we are just assigning this time periods in order to obtain them based on TA, TB, and TC. And what happens here is, since the zero, normally these are our voltage modulating signals, and this is our reference, right? But in this reference, when you see that at any instant the voltage might be positive or the voltage might be negative, and when these voltages have positive and negative values, then correspondingly these times will have positive and negative values as well. But we know that negative value of time does not make any sense, right? So in order to make all the value that are corresponding to this TA, TB, and TC as positive, we shift this reference axis from 0 to this level. And in order to make this shift happen, we add the minimum. This is the minimum, this much, this quantity, in order to bring this line from here to here, and then we add T0 by 2 in order to bring this line from this place to this place. So this is how we perform. So what we have done here is, we first I will add T minimum to this line so that it comes to this level, and then I will add T0 by 2 to this line so that it comes to this level. So in every cycle, I will calculate first the T minimum and T0, and then I will find the value of T offset and add this offset to all the three times that I have calculated here, so that I can obtain positive values of these times. So this is the basic algorithm of space vector pulse width modulation, where you calculate these times from the equations that we have just seen. We calculate the maximum and minimum of these values, and the effective, which is the time corresponding to active states. Okay, and the region. So T0 is the region which is out of the active states. So in order to obtain T0, you just subtract the T effective or the active state time from the total switching time of the carrier period, and then you calculate the offset time, and then you add these offset parameter to all the three times in order to get the time which is always positive. And then these times can be given directly to a comparator. In If we are going for a digital implementation, then it can be directly given to a comparator, compare registers or any kind of compare registers in digital mode, and then they can serve the purpose of giving us the pulse width modulated waves corresponding to space vector PWM. Another concept when you are giving the pulses to the switches is that when you have these, if you consider this leg, if there are two switches in a leg, then we don't want to turn both the switches simultaneously, right? Because if we turn both the switches simultaneously, then I am shorting the DC link. Basically, this is the DC voltage. And if I am turning both the switches on, I am creating a short circuit there, which is very dangerous for my circuit. The whole of my system will be damaged there. So I don't want that. And in order to prevent this from happening, we introduce a blanking time in between, blanking time or dead time. So that is the time where when we are so after turning on switch A, and before turning after turning switch A off. Suppose switch A was on before, and now I need to turn on switch A bar. So before directly turning so in order to turn on A bar, first I will turn off switch A, and after turning it off, I will wait for some time, and then only I will turn on switch A bar. I will not directly turn off the switch A and turn on the switch A bar, because that might give me a transient situation in which both A and A bar are on. This will be the state in between, which will short circuit my DC link, which I don't want. That is why I have to take care of this, and before turning the switch A bar on, I have to wait for some time after turning switch A off. So this is called a blanking time or the dead time. So while doing the pulse width modulation, you have to take care of that as well. So when you talk about analog implementation versus digital implementation, the same process is done, whereas in digital, all these calculations, the calculation for the offset time and the calculation for the maximum and minimum, all that will be done in a code part, that is inside a microcontroller or a DSP. Whereas in while we are doing analog implementation, you can do op amps for doing the this analog calculation. You can use op amp, triangle wave generator, Schmitt triggers, all these things in order to serve the same purpose. So you can implement this modulation technique, space vector modulation, using both analog and digital. And another thing, when you are doing this, when you're doing the blanking or the dead time generation using analog implementation, what you do is, instead of taking one carrier wave, you just take another carrier wave which is offset from the first carrier wave by some amount. So you give a small offset to them, and then this offset it gives you pulses that are having inherent blanking time in their waveforms. So you can see from this diagram here, it is very clear here that once you have given the offset, the carrier waves with offset, you will see that there is a inherent blanking time here, or the dead time here. So this serves our purpose of giving a dead time in analog domain. Whereas in digital domain nowadays, already DSPs and controllers have the provision where you can configure the system in order to have this blanking time. So the advantage of space vector modulation, so in sine triangle modulation, the maximum value that you are able to achieve is the per unit value, this one. Now, if you want to go beyond this value, then one of the approach that we do in space vector modulation is adding a third harmonic component. So when I am adding a third harmonic component, so initially this blue line was out of my league. I was not able to track it by simple sinusoidal PWM because it was out of my modulation range. But after adding this third harmonic component to the blue phase, I have got a new modulating signal, which is the red one, this. And you see that this red modulating signal is within the modulation limits. That means I am able to track a higher amplitude of fundamental with space vector modulation method compared to sinusoidal modulation. So that is the advantage of space vector pulse width modulation over sinusoidal pulse width modulation. So in normal case, if the range of sinusoidal pulse width modulation is 100%, then for the similar conditions in space vector modulation, the range goes to 114%. So in order to obtain this 14% extra, we chose space vector modulation over sinusoidal pulse width modulation. Now, uh, there are a lot of microgrids and sub microgrids available in our system. So, if you are given a choice that in your home, suppose you are supposed to make a microgrid of your own, and in your microgrid, you have a lot of water sources available, and you also have an ample supply of sunlight over there. So you have to choose between the two. In that case, where you have multiple options available, I have electricity also available, I have solar also available, I have hydro also as one of the options. Then in that case, how do you select which method is the most cost effective one for your particular purpose? And in what case which method should be used? And usually in microgrids, multiple options are available. So there will be one grid, and to this grid, solar will also be connected, wind will also be connected, hydel and thermal will also be connected. So depending on which is the most economic choice at that instant, we can switch from multiple sources. So in order to perform these actions, what we do is we make certain calculations first, and then we decide that which is the most cost effective source or the topology to be used and that particular application. So if you, again, as I mentioned, if you consider a sub microgrid, that is a very sub microgrid. An example of a sub microgrid could be your building, your multi. If there is a huge apartment building, and then they have rooftop solar or they have solar on the walls of the building, then you can consider that as a sub microgrid. My college has its own microgrid. We have solar panels in our ISC campus, and we generate certain amount of electricity wherever possible, and we use that electricity. So we have IIC microgrid, small I microgrid, and we monitor the data that our solar panels are generating and how much we are consuming. So we can call that as a sub microgrid. So to every sub microgrid, there are certain source ports, there are certain sink ports, and then there are bidirectional ports. So what are source ports? Any kind of energy source that I'm connecting to my sub microgrid will come under the category of source port, whether it is wind, solar, hydro, any such source. And sink port are the ports from where I am drawing the power. They are all the loads, lighting loads in our building, electronic loads, power electronic converter loads. All those loads will come in the category of sink port. Simultaneously, we always have bidirectional port for equipments like batteries. So we are all scared of power failure, or we cannot afford a power failure for sensitive equipments. So in order to serve that purpose, what we do is we always have a battery backup. So that battery backup is charged when we have ample of electricity supply, and it gives power to us when we don't have any supply. So therefore, it equipment like batteries are connected to bidirectional ports because we need to charge them when we have excess supply and we use them when we have less supply. Okay, so depending on requirement, this is a general block diagram of any kind of submicrogrid. Okay. Now, what there are certain issues with these submicrogrids. What are those issues? So there are a lot of sources. When you talk about a source port, the source could be anything. It could be PV, it could be wind, it could be hydro, it could be anything. So depending, irrespective of what kind of source I am connecting, my system should be able to perform, or my system should be able to handle the load. Now there are multiple things. The nature of load could be anything. It could be either a battery, it could be an uninterrupted power supply, it could be a front end power electronic load, or it could be simple lighting load. It could be anything, right? Now when you are making a microgrid of your own, that the most of the many of the microgrids are not connected to the grid. And normally in our electrical distribution system, the inertia of the grid comes because we have a very strong synchronous generators operating at some point. So we have these synchronous generators operating, and then they give power to our transmission and distribution system, and we get electricity from the grid. This is how our electrical system works. But when you talk about a microgrid, there is no synchronous generator connected to the microgrid. So when synchronous generator is not connected, which is having very high inertia, my microgrid is very vulnerable. My microgrid is subjected to any kind of instabilities. If I don't take care of my microgrid properly, then my it will be very easy for my microgrid to break down and become unstable. So in that case, what we do is we continuously monitor the THD. We have to take care of the wave shape. We have to connect special equipments to the microgrid in order to stabilize it. We have to continuously monitor. The quality aspects have to be ensured by ourselves. So we have to put certain converters in my microgrid that will act as the monitor for these quality aspects. So if my wave shape is not proper, it will be the responsibility of those converters to make the wave shape proper. Otherwise, the life of the loads and the working of the loads will be highly impacted. When I'm not able to supply good quality power supply to the loads, what happens is the life in the long run, the life of the loads reduce. Suppose with the if with like beautiful 230-volt 50 hertz supply, my motor was capable of running for 20 years. Then if I am giving it this power supply with a lot of harmonics involved, then the life of my motor might reduce to 10 years only. And we don't see these changes uh, happening in a very, like, we don't realize that this is happening, that this has happened because of the nature of supply that we have. Because of that nature of unawareness, we don't know that these things are important to us. But in actual, the quality of the power supply that we get impacts our electrical loads to a great extent. So we have to take care of that parameter. So we cannot avoid these things. Otherwise, we might run into a lot of problems and we might damage a lot of expensive equipment. Also, when you talk about microgrid, you have to think about grid extensibility. Grid extensibility means, suppose I have a building, and within my building I have solar panels and I'm generating a lot of power. In case I am generating surplus power, that means I am able to supply power to my building and I have more power left. In that case, I should be able to give that power either to the grid or to the neighboring building. I should have that capability. That capability is called grid extensibility. Okay, so these are few of the issues, very few of the issues. If you actually go and implement these, then there will be a lot of other issues as well. So these are just few broad issues that comes when you try to integrate or you try to lit up a sub-microgrid or microgrid. Now, there are a few examples to tell you the example. This example is based on integrated magnetics, and this will give you a very brief idea about how you can set up a microgrid using sub-microgrid using integrated magnetics. So, in this example, we are using something called a flux rate switch. So what happens here is you all have seen these cores, right? These are iron cores that we use in transformer manufacturing also. So suppose I take a few laminations of iron core and I connect a grid supply to it. And then to another set of winding, I connect this load. Then what I'm doing here is when I'm connecting the grid supply to this winding, this since the nature of the supply is AC, it will change the flux that is flowing through these iron cores. And due to the rate of change of flux from Faraday's law, we know that EMF will be induced across these terminals. And this induced EMF will flow through the current will flow current through these load and supply the power that is needed to these loads. Okay, so that is how this normal system will work. Now, in order to draw an equivalent of this diagram, you can imagine it as this. So, this grid is creating a change of flux, which we can call say d phi 1 by dt. So, d phi 1 by dt will be since EMF is proportional to d phi by dt, we can call the EMF source as d phi 1 by dt, and that will give this EMF generated will be given to the load. This is the green load we have here. Okay, this is an equivalent circuit. Now, uh, if if to this circuit I am connecting another voltage source here, then what will happen is initially I was generating one EMF using this. Now, initially this was my loop. Okay, this was my flux loop. Now I am putting another source here, so this will also generate another flux change, and let me call it as d phi 2 by dt. So both these flux changes, this grid will induce this EMF, this voltage will induce this EMF, and the both of these EMFs combined will give current to this load. So that is what we are showing here. D phi 1 by dt is generating one EMF, d phi 2 by dt is generating one EMF, and both of them together is giving supply to the load. Now, to this scenario, if I want to connect something else here, it cannot be a voltage source. Why? Because in particular loop, since it's a series loop, only one rate of change of flux can exist. Multiple cannot exist. Like we cannot connect two voltage sources in parallel and two current sources in series. Similarly, we cannot connect another voltage source in this particular loop. Therefore, if we want to connect something else, we have to connect it in current controlled mode. So we have to connect that converter in such a way that it acts as a current controlled converter. So when we connect the system as a current controlled converter, what happens is I am the current controlled converter and the grid together are now supplying power to the load. So the voltage, so the burden on the grid alone is reduced. Now initially, since if 100 watts of power was given by grid to the load, then in this case, let us say 50 watt is given by the grid and remaining 50 is given by the current control source. So the power burden on the grid has reduced, and the equivalent circuit for this particular circuit can be drawn as this. So now, since it is a current control source, its equivalent will be connected in shunt to the voltage source. Now, to this scenario, if I want to control the working of this circuit, depending on whether I have a grid or not, let me put this arrangement. This is called a flux rate switch. Now, what I am doing by putting this switch is, if I turn this switch on, then what I am doing is, I am making the voltage here zero by turning the switch on. The moment I make the voltage here zero, the rate of change of flux d phi by dt through this particular limb will be zero. D phi by dt will be zero. That means it will almost act like it is not connected. There is no limb here, right? In that case, the grid and this voltage will supply to the load. The circuit will be like this, right? Now, in case when I am turning the switch off, then the equivalent circuit will be something like this. And in this case, the part of flux will go into this limb also, and a part of rate of change of flux will go into this limb as well. So my grid will work along with the current control source and the voltage control source. So depending on whether my grid is present or not, uh, I can operate the flux rate switch in order to let the other two take responsibility. So when my grid is present, then current control source and voltage control source can serve other purposes. Like this voltage control source can work as a series compensator. This current control source can work as a shunt compensator. But in case my grid is not there, my grid is gone now. So in that case, I can use these to maintain the voltage across the load or the bare minimum purpose. Suppose the grid goes off, then flux rate switch will be used to remove the central arm from the picture, and then current and voltage source apart from the grid can supply to the load. In this way, you can make the system operate like a UPS when grid is not there. So this a small system in itself acts like a submicrogrid, where using the flux rate switch, I'm controlling whether I'm controlling the operation of the submicrogrid, what role these things will play in my system. So now if I want to apply the grid integration principle to this particular system, this was a current control converter here. So in order to write this current control converter, let me see, I have put this converter, and this is getting input from the PV module. The PV module will have DC output. This DC output will be converted to AC, and then this AC will be given to our submicrogrid system. And in order to give the pulses, suppose I am using sinusoidal PWM. Now this will be used for generating the PLL part, that is the row for my algorithms. Then we have already discussed the DQ reference frames. Then we'll set the voltage references, which will generate my current references here and here. And then again we'll have PI controller that will give me the modulating signals. And this modulating signals in DQ domain will be converted to ABC domain, and they will be given to the PWM block, and that will be inherently given to these switches that are present here, so that my current control inverter operates in the desired manner. Now to this current control converter, I can apply multiple topology, multiple algorithms. I could either focus on MPPT or unity power factor operation or harmonic cancellation. Any such aims I can focus, and based on that I will change these references, and my current control converter here will operate in such a way that I want. So if you want to operate with MPPT and unity power factor operation, then you will set these references. This is our MPPT loop. This MPPT loop will generate my ISD reference, and I will set ISQ reference as 0 in order to get unity power factor operation. But just by changing these input references, I can control the working of these current control converter here in the submicrogrid. And similarly, if I want to operate this as a series compensator, I can make certain changes, and by changing the references in the topology, I can make this system operate as a series compensator as well. So just the algorithm is the one controlling part. Otherwise, the hardware topologies almost remain the same. Now, as we mentioned, in order to compare multiple systems, if I have multiple options, how do I compare between them, whether to go for PV or hydro or thermal? So I have to have certain compare some facts on the basis of which I could compare. So, suppose PV modules in PV system, PV module have a lifetime of 25 years, and batteries have a lifetime of 5 years. Then we'll have to replace battery sets every 5 years, so that we could utilize the lifetime of the PV modules. So, a lot of subsystems are involved, and we have to make proper calculations that what will be the overall cost involved. So, in order to have a proper benchmark, in order to compare the multiple systems, what we do is we try to calculate the cost of 1 unit of electricity from different sources. That is rupees per kilowatt hour. We try to calculate what is the cost of 1 kilowatt power, or 1 kilowatt power of 1 kilowatt hour. What is the cost of 1 kilowatt hour of of energy when generated from different sources? So that cost is compared across different sources, and then we finalize which source we are going to use. So that process of calculation is called life cycle costing calculation. So when we calculate what is the cost of 1 kilowatt hour of energy from a particular source, we call that calculation as life cycle costing. Okay, so there is if suppose we have an item or any kind of product, and I am considering money as the basis, then with time the value of this item will change. It will either increase or decrease, and with time the value of money also changes, right? So both of these, the cost of that item and the cost of the value of money at that time, both varies with time, right? So the growth in value of item is called inflation, and the growth in value of money is called interest. So with time, I'm assuming that I am investing my money somewhere and with certain interest, and the value of my money will grow with time. That is my one assumption. Another assumption is that with time, there will be inflation, and the product or the item that is costing me 10 rupees right now, after 10 years, it might cost 50 rupees or 60 rupees. That is called inflation. So you have to consider both inflation and interest when you are making calculations, because both of these values change with time. The value, if the value of this item is 200 rupees today, and I have 400 rupees right now, 10 years down the line, the cost will not be 200 and I will not have 400 rupees. I'll have some other amount, and I'll have some other cost for this item. So that other values are to be calculated in order to do a futuristic calculations or comparison of these multiple sources. So you need to think through the complete cycle, because since a solar plant is implemented, suppose I am putting up a solar plant today in 2022. I cannot expect I am investing 20 lakh rupees. I cannot expect this 20 lakh rupees outcome within this year. I'll have to wait for a lot of time in order to achieve a break even point. Break even point means the point when the profit or the earning from this plant is equal to 20 lakhs. If I have invested 20 lakhs and I want my 20 lakhs back, I'll have to wait for 20 to 25 years, and then I will start earning profit. So this complete calculation from the start, and it might have an expiry, or let me assume that after 30 years I'll have to reinvest. So I have 5 years additional. So this complete 30 years cycle has to be taken into account while making these calculations. I cannot just make calculations based on what I have right now, because the outcome of these plants is dependent on time. So I have to consider the time factor. So in future, what will be the returns from this plant? We have to take care of those things. So so we have mentioned that there will be inflation and then there will be interest. So both of these parameters have growth profiles. That at what rate will they grow? They could grow at a linear rate. They could grow at a compound rate. They could grow at a exponential rate. So these are just three simple options. Then there are a lot of other models that are available in order to. So different products will have different model in practicality. So depending on what is the closest model for a particular product, we implement that. So when you talk about linear growth, this is a simple, like it's a example of a linear growth is simple interest. Suppose you have a zero amount of money right now, and you have interest rate of I after and you are considering n intervals. Then the sum after one interval will be S1 will be S0 times 1 plus I. Similarly, after 2 years or after two intervals of time will be S0 into 1 plus 2I. Similarly, this is a general formula for simple interest or linear growth. Similarly, when you talk about compound interest, so compound interest is comes in the product form. So it is based on the previous one. So when I'm calculating S2, I'll have to know the value of S1. When I'm calculating S4, I have to know the value of S3. So this is the standard formula for compound interest or compound growth model. Similarly, when you want to calculate the model for exponential growth model, you start with the compound model, that is called discrete compounding, and when you apply limits, the concept of limits to that, you will be able to obtain the formula for continuous compounding. So this is your formula for uh, exponential growth model. So based on what kind of growth model you're adapting, you can calculate these values. So when you consider, let us take an example. if you have an item and you have certain money right now, then let us assume that the value of my money is S naught and the cost of my item right now is C naught. Then after n intervals of time, if I have I rate of interest and I have F rate of inflation, then the value of my money after n intervals will be S naught into 1 plus I to the power n. If I am assuming compound interest growth model, and the value of cost of that item will be 1 plus F to the power n. And if after n intervals of time I need to still buy that item, then the profit that I make from my money or the value of my money at that after n intervals should be equal to the cost of that item after n intervals. So in order to purchase that item. So if I want to purchase, so this condition is this formula will be used in the case when I want to know what is the amount of value, what is the amount that I need right now in order to buy any item after n intervals of time or vice versa. If I need a relation between these two measures, then I can use this equation. And this is the basic example that sir has taken in order to demonstrate the use of this equation. Now, annual payment and present worth factor. So, if I assume that I have to make a payment, but I don't have all that money right now. Instead, if I choose to give that amount in installments, let us say I am planning equal installment, and the value of that installment is D amount. So, I am saying that after every year, I'll pay D amount. Then, what is the value of that installment that I need to pay if the cost of my item right now is given to me? So these kind of problems can be solved using the present worth and future worth factors. So we know that if we are considering compound growth model, then this will be our standard equations. And if I want to calculate the present worth, then this will be my factor because I will be talking about S0 for the present worth. And if I'm thinking about the future worth, then I'll be talking about Sn. So this will be my future worth factor. So based on these concepts, if I want to pay all these installment and I want to know in order to be successfully able to pay all these installments with the interest rate and the inflation, what will be the amount that I should have right now? Then I can calculate the impact of these at t equal to 0. And in order to calculate the impact of each of these, the present word that I need, I will be writing it like this. So this will be the impact of each of the D component right now. So in order to be able to pay my first year installment, I need to have D upon 1 plus I amount right now. For the second year installment, I need to have D upon 1 plus I ka whole square amount right now. So in order to pay all these installment, I'll have to have the sum of all these amount. So we'll apply a geometric progression formula, and after solving, you'll get this equation. And this equation, the factor that is present in this equation, we call it as present worth factor because this factor helps us determine if the value that help us calculate the amount, total amount that I need to have right now in order to be able to pay all the D installments that I'm planning. Okay. So if similarly, if I want to calculate D, then I can use the present worth factor and the S0 value in this manner. And this formula, same analysis can be done with inflation. Now, with inflation, another factor will come into picture that is 1 plus f to the power n. So, similarly, you can use the geometric progression and calculate the formula, and this would be a formula with inflation. So, if you talk about life cycle cost, then with life cycle cost, the components that are involved in life cycle cost are the capital cost. That is the initial investment done at time t equal to 0. Suppose I want to start a solar plant, I'll have to invest a lot of money. That is a huge sum of money. I'll have to purchase the land. I'll have to procure the solar modules, the power electronic converters, all the wire cables. Lot of I have to give money to a lot of labor. So all that comes in the category of capital cost. Now another component is replacement cost. So now I know that my battery has a life cycle of 5 years and my solar panels have a life cycle of 20 years. So every 5 years, I'll have to replace the batteries that I have in my plant. So that replacement cost adds up to adds up to constitute this component called replacement cost. Now then there is maintenance cost. So when I have a solar field, lot of dust is present there. So if I don't clean my solar panels properly, then I'll not be able to use them to their maximum efficiency. If the dust will cover the panels, I'll not be able to get the maximum output. So in order to get that, I'll have to employ somebody to clean my solar panels regularly. There are a lot of robots involved right now for cleaning the solar module. So that comes in the category of maintenance cost. Then there will be always fault, then replacement, transformer replacement, all these comes in the category of maintenance cost. Then there is energy cost. In order to keep this plant running, you will have to invest some energy. That is called energy cost. And then there is one parameter that comes back to us, that is called the scrap cost. So now after 20 years, if my plant is not, if all my things have, like all my panels have lost their life, they cannot work in an efficient manner anymore. So I'll have to replace all those panels, right? So when I'm replacing, all the old panels will be just waste for me. So if I have some mechanism where I can resell those waste solar panels or old solar modules to somebody who could extract silicon out of them or who could reuse them, then I will be able to obtain certain cost, and that cost is called scrap cost. So in order to obtain total life cycle cost, I add capital cost, replacement cost, maintenance cost, and energy cost, and subtract scrap cost because that is the money that I'm earning back. And these are all the investment that I'll have to put in between. Okay. So in order to look at the examples, sir has covered a lot of beautiful examples. So I'm just taking one that sir has given. So we have been asked to calculate the life cycle costing for PV based pumping system, which has this following data. So the cost of PV array plus balancer system, motor plus pump system, miscellaneous transport cost, pipe cost, and the cost of well. All these things are given. Now, all these things have different lives. So, we have to, in order to solve these kinds of numericals, you always start with a timeline. So, since you are asked to calculate for your plant is working for 15 years, so you can consider the period of analysis to be 15 years. And within that 15 years, every 5 years, you will have to replace the cost, and every 7.5 years you'll have to replace the motor and pump. So all these things, when you mark on this timeline and you calculate your capital cost and replacement cost in such a way, and the maintenance cost, and since the maintenance cost is installments every year, so you'll have to based on the D that you have, you'll have to calculate the present amount of money that you need to have to be able to pay those installments. So you'll have to use this formula that we just discussed. So when we add all these costs together, then you will know that this is the amount of money that I need to have right now. If I want to, if I'm planning to establish a PV based pumping system, in order to establish the system, I need to have this much amount of money right now. And if I am planning to have a loan sort of thing for this amount, then that will be called as annual LCC. So annually, how much amount for 15 years, how much amount I'll have to pay if I have to put this pumping system. So that is given by annual LCC, that is annual life cycle costing. So that amounts to 8,000 rupees. That means I have two options. Either I pay 61,848 rupees right now for this complete system, or if I don't have this money right now, I can do it in installment by paying every year an amount of 8,000. So I'll have to pay this amount of 8,000 for 15 years in order to make this make this PV based pumping system. So both these analysis, all these analysis you have to do, and come up with what is the most feasible solution for you, which kind of energy source you want to use. All these decisions depend on these parameters. If you have any doubts, you can ask them right now, or else we'll move on to the solution for the assignment. So let us move on to the solution for assignment number 12. So in assignment number 12, there are few questions that are still not resolved. So our discussion is going on with professor right now. So I won't be discussing all those questions. I'll just tell you what are the questions which are under discussion right now, and then you can see the solution for these questions in the solutions that you'll obtain. So in a day or two, they will release the solution for assignment number 12 on your portal. and then from there you can access the solutions to the questions that are under doubt right now. Okay, so yeah, so let us start with our assignment solution. So the first question is, for a three-phase, three-leg bridge, two-level inverter, what is the maximum possible value of the ratio of the amplitude of line-to-line voltage fundamental signal to the DC link voltage, adopting space vector pulse width modulation technique without overmodulation. So if you are considering space vector PWM, then if you go for the standard derivation, you will be able to obtain the ratio of line-to-line voltage, the line-to-line voltage to DC to VDC as 1 per unit. Similarly, for if in this question they have asked you for sinusoidal PWM, like they had asked for space vector PWM. So if you do the similar calculation from sinusoidal PWM method, then V line to line by VDC amplitude will come out to be 0.866 per unit. These are very standard derivations you can find anywhere. And if you have any doubts, you can let me know. I don't have time to discuss them right now, so I am directly giving you the answers. But if you have any doubts, you can reach out to me. Yeah, so this is one of the problems that is under doubt right now. So you can look up for the solution. Okay, so this question and fourth question. So both these questions will be discussed later. Okay. If you have any doubts from the solution that you are not able to understand, you can put on the forum. They'll reply to it. Okay. So yeah, the fifth question we can take right now. In fifth question, for the data that is given in question number 3, what is the annual installment to be paid in rupees if it is calculated with compound interest approach? So in the third question, the data that is given is there is a solar panel which is costing rupees 2 lakhs. Okay, and the interest rate is given as 8.5% and the time interval is given as 3 years. Now, when you consider the compound interest approach, and you are asked what is the annual installment to be paid. That means they are asking us to calculate the amount D when you are given the cost of that panel at that very instant. That means this is given as S0. That means I know the cost of my product right now, but suppose this is my time instant 0, this is my timeline, and these are my, okay, 3 years only, right? This is my first interval, second interval, third interval. So at the end of this time, if I am paying out D, and D amount of installment, then and I have given S0 cost. Then what will be the cost of these installment that I'll have to pay? That is what they have asked us. So we know that there is a standard formula where S0 is equals to D by I into, if you just put N is equals to 3 and I is equals to 0.085, then and S0 is equals to 2 lakhs, then D is equals to 78,308 rupees, okay, approximately. So this is the solution for this problem. Now let us move on to the next problem. Problem number 6. What is the value of an item in rupees after 10 years? So there is an item and there is a timeline again, and this is 10 years. So this is, let me see, this is 0. What is the value of an item after 10 years? So S10 is being asked if the present value is rupees 7 lakh at an inflation rate of 7.5%. And we are being asked to use the exponential growth model. So for the exponential growth model, if we talk about, then we know that Sn is equals to S0 into e to the power In, where I is again the interest rate and n is the time interval. Similarly, therefore for n is equals to 10 years, S10 will be equal to S0 into e to the power 10 times I, where I is equals to 0.075. So if we just put this value, then S10 will come out to be S10 will come out to be 1,41,900. Sorry. Yeah, this is the value. So this much is the amount that will have to pay if the after 10 years if the inflation rate is 7.5% and we are following exponential growth model. Now problem number 7 and 8 will be confirmed in the solutions. Okay. Uh, so let us discuss problem number 9. So in this problem, a PV array shall be installed for a domestic application. Its capital cost is rupees 1,50,000. So it's given capital cost as 1,50,000. And the life of the PV array is 30 years. The annual maintenance cost, let us say AMC, is equals to 750 per year. And calculate the life cycle cost of the PV array. Consider scrap cost of 10,000 rupees at the end of its life and at an interest rate of 10% on maintenance charges. And they have asked us to ignore the energy cost. So we have to calculate the life cycle cost, and we are given the capital cost and maintenance cost and scrap cost. So we know that life cycle cost is equals to capital cost plus annual maintenance cost minus scrap cost. So these are the only parameters that are given. Okay. So straightforward capital cost is 1,50,000, and for the annual maintenance cost, and we'll have to it's 750 per year. So the amount that we need right now is will be given as d by I into 1 minus 1 by 1 plus I to the power n, and scrap cost is 10,000 rupees, right? And we know that this will be our LCC. Now we know that D, that is the installment that we have to pay, 750 rupees, and I is given as 10%. That means okay, so I will be 0.1. Okay, so when you just put these values, and n will be equal to 30 years, because we are looking for a life of 30 years. Okay, and scrap cost will be available at the end of 30 years only. So life cycle cost will come out to be when we just put these values, 1,47,000. This is the life cycle cost. Okay. Now, in the next problem, they've asked us to calculate annual life cycle cost of the solar panel discussed in earlier question. So, if I don't have the life cycle cost amount that I just calculated, 1,47,000 if I don't have, and I have to pay it in installments for next 30 years, then I know that annual life cycle cost is equals to life cycle cost by present worth factor, right? And present worth factor is given by 1 by I into 1 minus 1 by 1 plus I to the power n. So we have already calculated the value of this factor, and it was 9.4269. So this amount comes out to be 15,601 rupees. So either pay upfront rupees 1,47,000 to install this PV array, or pay 15,000 for next 30 years. So you have these two options. So this is the significance of annual LCC. So that's it for today's discussion. If you have any doubts, please you can ask right now. And all the questions that have been remaining from this session, we'll take this. You can look at the solutions in the assignment solutions that will be provided in within next 2 to 3 days. And if you have any doubts, then you can ask on the forum. and probably this is our last session. So if you have any other doubts, you can write to me, or you can, or yeah, you can write to me for any doubts. And if you want to revise, I am sharing my email ID. Okay, so this is my email ID. I am sending in the group, and you can visit my YouTube channel if you have any doubts. So this is the link for my YouTube channel. Okay, so all the sessions that have happened so far are mentioned on this channel. You can revise them from there, and I wish you all the best for your exams. Okay, thank you guys. Have a nice day.